This is the machine learning course. And today, our goal is to finish all this probability review. And starting on Thursday, we'll actually get into supervised learning and stuff. So let's do that. Okay, quick little reminder of what we did. So we're trying to just formulate this whole idea of what it means for this data set thing to be randomly sampled from some distribution and to be independently randomly sampled. And then what is that going to imply for the fact that our learner is a function of this random variable, the data set, and then it's going to produce a predictor. And then the predictor, okay, it's going to take in like features, but we're going to see these features can be like any new feature, which you can think of as just like any new random house that you're going to get. So a lot of things are going to be random here, and we're going to need to understand how to deal with these things. And that's what we're doing. So yeah, there was this whole example with the rod and the masses and so on. You can watch the last lecture about that. But the story was that, like, you want to talk about the probability of events. Events are just going to be some subset of outcomes. And the way you do that is you plug it in to some probability distribution function, and it tells you the probability of that event. And then this thing is kind of complicated because there's a lot of events, especially if your outcome space is like the natural numbers. There's like, countably infinitely many subsets of the natural numbers. So how do we like solve this problem? And this is solved by finding out that we only really need to talk about the probabilities of kind of like the events that contain a single outcome. And that's what the PMF function tells us. It tells us like what's the probability of a single outcome or the event containing that single outcome. And that's what happens for these discrete random variables. So we have this PMF. That's really all you need to know. It's like when you want to calculate the probability of something, if it's discrete, your random variable is discrete, this guy here, you use the PMF, and then you calculate things. And if your random variable is continuous, which means that its like outcome space is going to be uncountable, and it has this property that the probability of any single value occurring or any outcome occurring is 0, well, then you need to use a PDF, which is like telling you the density at every point. And so there you would talk about like the probability of events that are like intervals, basically. Yeah. So that's what you need to know. PMFs allow you to calculate probabilities for discrete random variables. PDFs are these things that allow you to calculate the probabilities for continuous random variables. And yeah, with PDFs, you integrate. With PMFs, you sum up over the corresponding outcomes. Okay. And then there was various famously known named distributions like the Gaussian, which has this density. Okay, so this is kind of where we got to last time, and then we started talking about, well, at the end of the day, you may want to talk about more than one like random like experiment happening and so on. Like, for instance, you might want to talk about like, what's the probability you flip a coin and get heads, and you roll a dice and get the number 3 at the same time, okay? And obviously this is going to be important for this whole supervised learning thing, because you're going to be like, well, what's like the probability that, let's say, one of my features is like exactly 4 rooms and then 2 washroom house and also being 10 minutes from the university. I don't know, but it's going to be something. Okay, so we want to talk about the probabilities of multiple random variables. So we kind of do the almost obvious thing, which is we define a new random variable, which is just a tuple, such as this, x, and you just put the other random variables, like, let's say 2 coin flips, as a tuple inside this thing, and then you do everything kind of the same as before, more or less, where, the outcome space is now going to be all the, like, ordered pairs, or if you have, like, 3 things like this, so here your outcome space is like the natural numbers, Cartesian product with some interval and another interval, you have, like, you end up with, like, a set of ordered triplets or tuples with 3 entries. And they look like this. Yeah. Okay. So that's this joint or multivariate random variable stuff. And it has a corresponding distribution described in the same way, which is you have yeah, it's going to talk about the distribution of events, which are now subsets of this like slightly more complicated outcome space. And the way you're going to calculate things is, again, through PMFs and PDFs. And you're going to have like PMFs over joint random variables and PDFs over joint things. So here's an example. You have like this random variable z. It's just a tuple of two random variables, which each are discrete. And just to know, we're going to like do the case where the like random variables are all discrete or all continuous, and then we'll get to the case where they're mixed, and we'll see how to deal with that in maybe about 20 minutes. Okay, so this is a case where things are all discrete. And so if all of your random variables are discrete, and yeah, then you have a PMF, and it's like it's a joint PMF, and it's going to tell you the probability of any single outcome. So that would be like the probability of the first random variable being 0 or the second probability random variable being 0. And the running example we're going to have here is that our first random variable x is going to represent whether a person is old or young. So young is like the smaller value 0 and old is going to be 1. Those are the two possible outcomes. And then the person is either going to have or not have arthritis. So 0 for no arthritis, 1 for, I guess, positive for arthritis. So we're going to do this is going to be like a running example to kind of build some intuition throughout. So I guess keep these in mind. So X is young, Y is arthritis or not. Okay, so like the PMF tells you the probability of any particular outcome, such as the probability of being young and not having arthritis. And that's just going to be a value. And so to talk about the probability of any event, you just need to define this PMF, which means define the probability of the 4 possible outcomes, which is all we're doing here, right? So there's this outcome, there's this outcome, there's this outcome, and there's this guy, and you define the probabilities. You got to make sure they sum up to 1, as we discussed. And then you can talk about things. And visually, you can think about it in various ways. You can write the like X and Y as this kind of like table of values they take. So X takes 0, 1, Y takes 0, 1. And then in these squares, you can kind of write in their probabilities. This is just like another way of writing literally the input-output mapping of a function that has in like 2 variables. Maybe the more productive way to think about this is going to be in terms of like kind of the areas that these probabilities take up in like a unit square. So you have like a unit square here. So this thing has unit area. And I'm going to partition it based on the probabilities of things. So this outcome 0, 0 has probability assigned 1/2. The outcome 1, 0, which is like you're old and don't have arthritis, has probability 1/10, which visually should be taking up 1/10 of this square. And then, yeah, the other 2 also fill in the things, and we'll see. These are this picture is going to be quite important for like getting some intuition for how do we talk about different things. Okay. And so now here's an example. I might ask you a question like, you know, okay, I give you the PMF, so I could like I literally just give you these 4 values like this, let's say in a question. And then I ask you, like, you can ask it as a word problem, which is like, what's the probability of, let's say, just being young, right? Well, then you'd be like, well, what's the event of just being young? That's like the only thing I like maybe care about. And so that event you would write down as like this. You'd be like, oh, that's the event that, you know, I'm young and don't have arthritis, or I'm young and I have arthritis. Those are all the cases in which I can be young. And then you can talk about the probability of this event. And the way you're going to do it is by talking just about, you're going to basically notice that this is like the union of 2 outcomes, the set of 2 outcomes, and then you just apply this like PMF trick that we saw before. Okay, so like the probability of this event is just going to be the sum of all the outcomes in the event of this PMF thing, right? So this would just be like the probability of this thing plus the probability of this thing. And then I showed you that like there's this other way of writing summation notation when you have 2 variables. You write this like double something. It means the exact same thing as we saw here. And it just means like sum over the values of y and then over the values of x. And so yeah, you get this thing, as you would expect. Like it's just the probability of the 2 things. And if you look in the picture above, that's just like 1/2 plus 1 over 100. And that's where we ended off last time. And visually, it's going to be like, you know, you take this area, that's you being young, and the other place where you're young is this little guy here. And you just put them together, and like that turns out to be 51 over 100 of the area. Okay. And this has a name, this idea of like you only care about one of the variables. This is called marginalizing. Okay? And so we have specific symbols to describe these distributions over only one random variable. And these are called the marginal distributions, and there's going to be marginal PMFs and PDFs as well. So if you want to just talk about the distribution over some like subset of the random variable, so in this case just the single random variable x, which is whether you're young or old, well then people like to define a new distribution based on the joint one in the way that we just did in a second. So let's see how this works. So a marginal distribution tells you what variable are you going to be talking about. And so like you write something like this. So you take P and then you write a little subscript being like, oh, I want the probability of just the random variable x. And then, yeah, and then you talk about events that are only over the outcome space for which that random variable x lives on. So this would be like this outcome space in the arthritis example will just like 0 and 1. Okay. And to calculate these things, we're going to have marginal PMFs. And we write the little random variable to tell you this is the marginal PMF for the random variable x. And you calculate, okay, so what is this thing? Well, the way you get this marginal PMF, right, that's going to help you calculate the probabilities is the following. So, right, you start with this joint PMF, that's what you're given. And then you're like, okay, like all I care about is the probabilities of x. I don't really care about y. So what you do is you say, well, this like probability of just the outcome x, they're all just going to be like the joint, but I don't care about y basically. I'm just going to sum up all the cases for y. So in that arthritis case, it was like, you fix this thing, which was like you cared about being young, and then you're like, okay, let me take all the cases of the other random variable, which was to have or not to have arthritis, and sum up those probabilities. That was exactly what we saw here. We fixed this thing, you're being young, and then you summed up the other things. Okay, and that's just the general way to get these marginal things. You're just going to like sum up the PMF, the joint PMF over all the other random variables you don't care about. And hopefully that makes complete sense. Like you don't care about those things, so let's just, not care about them and take their probability and add them all up. Okay, and as we saw, like you can let's calculate this marginal PMF for the example we saw earlier. So, right, this okay, so like the distribution of x equaling to some value is just the same as the PMF with that value plugged in here, and that's just this sum that we saw over here. So it's just like you plug in 0 here. This is like kind of okay. It's x in the same, like this set is just the same thing as x equals 0, right? So that thing's 0. I don't know why I even wrote this thing, to be completely honest. There's no x even being summed up. Okay, that's what it should be based on this definition, clearly. And yeah, so we sum up the two values of y as we saw, which is 0 and 1. We get this 51, and visually this is like the orange thing. So once again, this picture is going to come in handy. And then like visually, you can see obviously what's going to be the PMF for x equal to 1. Well, that's going to be this green thing. And so what you do is you sum up those two probabilities and you get this 49 over 100. Okay, great. So now we know like what's the probability of being young or the probability of being old. And they're roughly half and half. I don't know how people like, this is obviously not a real example, but yeah. Okay, so now the like more general case is you can have many random variables like x1 to xd. You can have a multivariate random variable over all of these, right? So you just put them all in a tuple. You call that capital X. And this has the outcome space of like all those random variables, outcome spaces Cartesian product. So this thing is the set of tuples for which the tuples are of length d and take values in each one of these outcome spaces, right? So like this ordered sets of d objects. And then, yeah, so in general, this is like you can have these large joint multivariate random variables. And then you can talk about like their PMFs, their joint PMFs, like that thing. And then you can also talk about the marginals, which is just saying like, I only care about one random variable. And that's gonna be enough for this course. In general, you could talk about like, oh, I only care about 2 or 3, but we'll just do the case where you care about one, and what happens is you just sum up over all the other random variables, and you get that PMF. So what does this look like? It's like, if I want the PMF for random variable xi, which I don't know, maybe describes some property, only one property you care about, like maybe the house's age. Well, then to get that PMF, you take the joint PMF and you sum up over every other value. So you're going to sum up over x1 up to xi minus 1, and then xi plus 1 till xd. So that's what all these sums are. And you're not going to include the sum for xi, because that's the thing you care about. And that will give you like the probability of that particular outcome for just that fixed value. Okay. And so, yeah, once you get this thing, you can then you can just use this marginal PMF to calculate the probabilities of different events in the same way as before. If you have some event, you just sum up all the outcomes in the event. Well, you sum up the PMF of all the outcomes in the event. Okay, and so maybe for like reference, how this is going to be used is someone will come to you and be like, oh, like here's this like joint PMF. I know like the probabilities of all these things. And then you're going to be like, oh, okay, great, but like I only care about, let's say, the probability of the number of rooms in the house or something. So then you like, just for ease, really, you construct this marginal PMF here, and then you're going to use that to talk about that, because you don't care about the other things. Okay. And so this is for the discrete case, there's sums. And you can imagine for the continuous case, there's just going to be integrals. And your random variables, for which the multivariate random variable is based on, they're going to come from like these uncountably infinite outcome spaces. Yeah, so continuous random variables, that means these x1 till xd are all continuous. So then you'll have a continuous multivariate random variable. And notice so far we're still dealing with this case where like all of the entries are either continuous or discrete. And then same exact story. So you just like, if you care about the PMF or like really the probability of just like the single random variable's outcome, well then what you do is you integrate out outcomes x1 or like calligraphic x1 till calligraphic xi minus 1. You don't use the integral of xi because that's what you care about. So there's like somewhere in here, there's, you know, xi. That thing you're not going to touch, and then you're going to integrate out the rest of the stuff. And then if you want to calculate the probability of some event, you do the usual thing, which is you integrate over the event and you integrate the density here. I don't know if I was saying PMF, but these were all joint densities, and these are joint, this is a joint density. This would be like the marginal density of xi, or PDF, the probability density function. Okay, great. So far we've talked about this case of like, maybe you want to talk about one random variable. What's the probability of it, but you have this joint thing. Okay, this joint PMF or PDF is going to give you the ability to talk about more than just like the probability of a single thing. You might want to talk about, well, you know, like what's the probability that I have arthritis given that I'm young? Or what's the probability of arthritis given that I'm old? And so these are called conditional distributions. And the conditional part is that you're conditioning on some other outcome. Yeah, so let's do the example. Okay, so like the probability that I have arthritis given I'm young. So I guess I tell you some definitions, and then we're going to work it out for that arthritis example mathematically and visually with that diagram. So the way this goes is, you have this, like, you have some random variable, let's say y, and x now. Okay, well, this is the same as we saw before. And so the conditional probability is going to be defined through its conditional PMF or PDF. And so what is this conditional PMF or PDF? Well, it's going to be based on the joint, right, as we saw before. And this is what it's going to look like. This is the definition. So the probability of getting some outcome y conditioned on the probability of on the outcome x is going to be the probability of x and y happening divided by basically the probability that just x happened. And in some way, well, you'll see visually this is going to clarify some things, I think, but you should think of it as like, okay, I only care about the case where x happened. So I don't care about like any like a particular x happening. So I don't care about any of the others. So I'm going to divide by this smaller probability. And then only in that scenario am I going to talk about the cases where y happens. So yeah, we'll see this in an example in a moment. And so the way, yeah, same story as always. If you have this conditional PMF, well, then you can calculate the corresponding conditional distribution through it using the classic, you sum up over all the outcomes. So you're seeing this theme. All you need is the PMF or PDF. And then depending on what you care about, you're going to need like the conditional or the marginal or the joint. And that's depending on the thing you care about. And for continuous random variables, the story is the same. But you just integrate and you have a conditional PDF. Okay, so let's get into the example first, and then we'll come back to some of these other properties. Okay, so let's say I care about the probability that I have arthritis given that I'm young. Well, let's look at it visually. Like, what would you think this would be, right? So it's like, remember, this is the part where you're young, because you have the first outcome is 0, and here the first outcome is 0. The green part is the probability that you're old. And I only care about the case where I'm young. So clearly, I should only talk about the orange region, because that's like what conditioning should mean. Something like, I'm only going to care about this region. Okay, so now I've kind of like restricted myself to the orange region. This is what it's going to do. We'll see how that happens in a second. And then what do I care about in that orange region? Well, the thing I'm going to care about is that I have arthritis. And so, okay, this is the case here where I don't. This little region is the case where I do. And so kind of naturally, I'm going to care about this ratio, which is like how much of this orange area is occupied by the outcome I care about, which is, right, having arthritis here. And that's what this division ratio does, right? So let's look at the calculation. The calculation is like as follows. So you have to get your conditional PMF. Okay, that's what this object is. We're going to expand what that object is next. And we're going to care about, right, the like event that y is exactly the outcome 1. Okay, and so now this is just the same thing as this. I've just removed the sum because there's just one outcome in that event. And now what is the definition of this object? Well, you go up and you look at it, and it's this ratio thing. So I just write it out. So that ratio is going to be the joint, right, of the two values. It's going to be like 0 and 1, being young and having arthritis. And that's this little region. That's that probability. And then in the denominator, you have the marginal, right, which tells you like the probability only for like a particular random variable. And that's going to be the one you conditioned on. And so now we have to use the formula for the marginal here. And what's the marginal formula? Well, it's you fix this for the corresponding random variable x, and you sum up over the other one, which is like the arthritis random variable. And so you get this. And what is this thing at the bottom, right? This is like the orange region. It's exactly, so yeah. So then like what happened here is then, okay, then you plug in your numbers, and you get that the probability that you have arthritis given you're young is 1/51, which is exactly the like ratio of this area over the whole area. Okay, so hopefully that should make sense. You can, another way to like maybe commonly think about this probability stuff that is kind of helpful is you notice when you like, when there's all this division and stuff, these like the total, like this ratio, if you write things as fractions over 100, then the fractions will always cancel. So okay, when you write the final thing, the fractions will cancel. And so you can kind of think of this as like, you know, if you had 100 people, if you had 100 people, this is like your maybe full area. Well, then maybe 50 of them, this represents kind of like 1/2 of them, 50 of them are in this case. Here you have 1/100, so like one person is this case, and then whatever. And so all this is telling you is like 1 out of 51 young people are bound to have arthritis from this case. Yeah, which is this picture here. I guess you basically have like reduced your space, you reduce your area. And okay, and so you can do the calculation for any, you can like change the young from 0 to old, which is x = 1, and then you would do the same thing for this green area. And that would be like, we can visually look at it. It's like, oh my goodness, when you're old, the chance you have arthritis seems to be much, much, much higher than if you'd been not having it, right? And so you'd be like, oh, okay, that seems to be different. It seems to actually depend on if you're young or old. Okay. And there's two more Okay, so we're going to do that. We can do that calculation. You can actually flip the random variables and be like, well, what's the probability that I'm young? So that would be down here. What's the probability that like I'm young? So that's X equaling 0, given that I have arthritis already. So someone's like, oh, like you have some data, some people have arthritis, and you'd be like, well, what's the probability they're young? And you can reverse them. And so we're going to do this through like a property that I want to mention that people seem to like to give a special name to, but really it's nothing special. So you see this equation up here. Well, you can obviously, use some very deep mathematical facts of rearranging things. And you can move this thing over here to the right-hand side. And you can move that to the right-hand side and you get the following expression, which sometimes people call the chain rule. And so now you get that like the probability of X and Y happening can be read as the probability of Y first happening, and then conditioned on the fact that Y happened, what's the probability that X happened? And it turns out this property, you can just keep doing it in general with more and more of these kind of random variables, and it looks something like this. So if you have many random variables, you can chain them all together in this way, and you are to read this as the probability of getting x1 and x2 and xd as exactly these outcomes is the same as the probability that I got x1, and of course, this is like the marginal of x1. I forgot that there. Okay, maybe I put it in green. And then times the probability that, conditioned on the fact that I got x1, that I got x2, right, x2. And this is, of course, like the conditional of x2 given x1. And then it's like, oh, I already got x1 and x2, so now what's the probability of getting x3 given that? And you keep repeating this over and over until you get all the way to xd, conditioned on everything before. And so these are equivalent, and sometimes it's a lot better to think about things in the following way. Okay, so that's one property, literally just rearranging things. And then there's another thing called Bayes' rule, which is you take this equation, you look at the guy over here, the guy in the upstairs, and you're like, well, okay, I know that, this thing up here, I can write it in this way or the other way, choosing whichever way you want. And so I just replace it with that chain rule step up like that I had before. And so that's Bayes' rule. I don't know. Turns out to have a name. And why would you kind of care about it? Well, you might care about it because maybe you don't have this joint PMF or PDF. Maybe you only know the probability of Y given X and the probability of X and the probability of Y. And if you only know about these, but you don't know the joint, then you can still do the calculation. So, in a homework problem, you might see something like, I give you this conditional, these two marginals, and then I ask you to calculate something like this other conditional here. And you don't have the joint, and you're going to have to use this formula. And this is, I guess, the thing I wanted to point out is you see above, we are missing subscripts because these are different functions. We're missing the X here, we're missing the Y here, and this is just common. So from now on, when you based on the input values of your function P, you should know which function we're talking about. So that's what this means. And this is technically just abusing notation, but it's done a lot of times, so you don't have to keep writing these subscripts everywhere. So based on input types, you should be able to parse the corresponding function you're using. Okay, so back to the arthritis example. One way to calculate the probability that you are young, given you have arthritis, is to actually just use Bayes' rule. So you first note that this is just equal to this PMF, and then you just plug in the formula for Bayes' rule. And why is this kind of nice here? Well, it's nice because when you plug it in, we already calculated one of the quantities above, like this guy in the example here, and these other two marginals are, okay, maybe you have them or are easy to get. And so you get 1/40. Okay, well, okay, so you got this thing, and let's just intuitively understand this through the picture. Does this match what our intuition is? Okay, let's see. This is the probability of being young given I have arthritis. So I'm going to go up here, And I'm conditioning on the fact I have arthritis. So that's like the second outcome being 1. So what is that going to be? That's going to be like, here's the case where I have arthritis, and here's the other case where I have arthritis. So that's this region here, this whole square. You can see that total probability is 39 over 100 plus 1 over 100, so that's 40 over 100. Or you can think like 40 out of 100 people have arthritis. And then you care about the case where you're young. And that's this little region here. Only one person, it satisfies this, or like that's the probability of that. And so the ratio of this, like 1 over 40, is the probability of being young given you have arthritis. And so obviously, like visually, this is nice to do when you have like 2 random variables. But when you have more, it's going to be very hard to draw these pictures. And so then you use these general properties. Okay, great. And so naturally, this kind of leads to the fact, another thing that you might want to talk about, I guess, between these things, which is like, is one outcome, like one random variable, kind of independent of the other? Or does it depend on it? And mathematically, it's written like this, which is that the joint 2 random variables are independent if their joint PMF can be written as the product of their marginal PMFs. Okay. That maybe is not like super intuitive. So let me give you another way to think about this. So the joint PMF can be written using the chain rule as follows, right? It's like the probability that I got Y, and then conditioned on Y, the probability I got X. Okay. And I just told you that the property, okay, well, let's derive this property in a second. So it's like, okay, what does it mean for something to be independent? Well, it's probably like if I condition on that other thing, it's not going to affect me at all. So it doesn't matter if I had arthritis or I didn't. I'm just like, okay, well, in the arthritis case, it's going to matter. But let's do another case like where you flip up 2 coins. Well, like the probability of getting the first coin flip shouldn't matter what happened in the second coin flip. And so that idea is like this conditioning shouldn't affect anything. So in other words, this conditional PMF should be exactly equal to the corresponding marginal PMF. So that's what this property really is saying. And you can do it the other way around too, right? You can always write the joint as the marginal times this conditional, and this will say the same thing. So if Y is like independent of X, then that actually implies that X is independent of Y based on this, which is, yeah. So that's kind of cool. And so, yeah, you can imagine we extend this to more generally to more random variables. And now you can kind of see we're getting into like the data set and stuff examples. I said things like maybe we have n houses that are gathered independently of others. Well, what that's going to mean is something like if you have these, well, here you have d random variables. Them being independent is going to mean that their PMF can be factored in this way, which is you can write it as the product of all their marginals. Yeah, and that should have the same interpretation. If you write out the chain rule, right, there's like all of these conditional things. So let's just go up to see that. If you write out this long, complicated chain rule thing, which is this, the fact that you can write it as the product of all the marginals just means every single guy here can be written as like, oh, this is the marginal of x2. So I don't care about x1 at all. And this is like the marginal of x3. It means I don't care about x1 or x2 at all, and so on. So this would be like the marginal of xd. So that's what that's saying. So that should make some sense as well, hopefully. And so now let's see some examples of how that will look like for the arthritis case, and see, is the arthritis example, is like you having arthritis independent of you being young or old? And like intuitively, that's probably not the case. And in the example I gave, it turns out to also not be the case, but let's mathematically see that. So how do we do this? We say, okay, let's look at, all we have to do is just show that the joint TMF for any particular input does not factor into the products of the 2 marginals. So I chose a particular one, which is like the probability of being young and having arthritis, right? And we know what that is. We calculated it, or actually, we didn't even need to. We were told it, which was, this is 1 over 100. And that was like that little square in that picture we saw. And the claim is, if they were independent, I should be able to just take the probability of being young and the probability of having arthritis and multiply them together, and I should get the same probability. But if you do that, you do not get the same probability. You actually get 0.2, or like, this is something like 20, almost like 20 over 100. So that's quite different from 1 over 100. So this is how you, if someone asks you, like, they give you this, let's say the joint PMF, and they're like, well, are these random variables independent? Well, you have to go and search for some outcomes that don't satisfy this if you want to show they're not independent, or if you want to show they're independent, you're going to have to show that that they do satisfy this for all possible outcomes. So let's see an example of things that are independent, and that's this 2 coin flip example. So let's suppose you have random variables x1 and x2 representing the one coin flip, and then the second one representing a second coin flip. They're both fair coins. Visually, you can see it in this table. So what happens is I might give you this joint PMF being well, the probability of getting heads and heads is 1/4, and tails and heads is 1/4, and so on. They're all 1/4. They're all fair coins. And then you would find that, oh, indeed, these coin flips are independent because they do satisfy the property, which is for any x1 and x2, the probability is 1/4, the joint probability. And this is exactly equal to the probability of just getting x1, some value, which is 1/2, times the probability of getting x2 as some other value, which is also 1/2. This is the probability of getting, let's say, heads or tails, and the other heads or tails, and that's also 1/4 at the end. So this mathematically shows that things are independent, as we would intuitively expect them to be. All right, so now we can handle, okay, let's handle this case. There's 2 things that's going to happen next, which is we're going to talk about how this applies to the data set that we're working with in machine learning. But before that, apparently I decided to address another problem, which is what happens when you have a multivariate random variable of, let's say, 2 random variables, x and y, but y is discrete and x is continuous. Right? So what's going on here? Because I told you, oh, if all the random variables are discrete, then you have a joint PMF. If all the random variables are continuous, then you have a joint PDF. So what happens here? Now what happens here is the actual answer is that, if you did all this stuff in measure theory world, you wouldn't have any of these problems. But we simplified things with PMFs and PDFs and so on. And you do kind of run into these issues, as we can see. But it's resolved using the chain rule, because it turns out, right, if you have any joint thing, I don't know what this is some mixed thing. I can't really give it I can't call it a PMF or a PDF. Well, it turns out that thing, actually, you can still use the chain rule, okay? And that's just a claim you're going to have to take for granted that is true. It turns out that you can still write this object, and it's going to satisfy all the properties you want using this chain rule property. And now so we get something like this, right? Which is this joint object is going to be written as sometimes people call the chain rule the product rule. It seems more common to call it the chain rule, so I changed it to the chain rule this year. So that's also, I applied this chain rule. And so I can now break it up into the probability over just kind of the random variable x, and the probability over just the random variable y conditioned on x. And now it turns out that, well, these are just kind of really PMFs or PDFs over single random variables, and then we know how to work with these things. And so, for instance, I gave an example here. So okay, which one was what? Let's see. Okay, apparently I chose one to be, did I give, okay, I don't know what. I just chose something. So, oh yeah, here, never mind. This is how it works. X is continuous, Y is discrete. So based on that information, I know that the marginal of X is going to be this PDF, right? It's continuous. So this guy here, this marginal, is going to be a PDF, okay? And this conditional guy, since Y is discrete, so every time you fix an X, you're just talking about Y's, distribution over Y's. And since Y is discrete, for every fixed X, you get a PMF, right? Okay, and that's gonna help us do calculations, obviously. So let's do an example with this whole wine business that we saw maybe from the first class, which is you have, let's say, the amount of some chemical, And so here, instead of two chemicals, we just have one. You're just given like the amount of some chemical. That'll be this random variable x. And let's say that chemical's quantity can be between 0 and 900, I don't know, grams or something. And then your y, so that's continuous, right? Just the amount of that chemical. And then y is like the type of wine. And here we're going to have this like binary, I guess, outcome space, which is either it's not the Barolo wine or one for it is the Barolo wine. Okay, so now let's see how this calculation might work. So I might then like someone might tell you, oh, okay. So I gathered my features, X, which is the amount of chemicals uniformly. Like I sampled, or I gathered them from like this uniform distribution over 0 and 900. So that means that like your data is kind of like going to look like, okay, we're not going to talk about, but like that means that this PMF of like just the X, the chemical, is uniformly distributed. So the chance you get any amount of chemical is equally likely. So there's like, yeah, so the density is 1 over 900. So it looks like this. And if you integrate this like area, you get 1. Okay, so that's maybe reasonable. Maybe that's like a reasonable way to gather these features. And then someone tells you that, well, the conditional of y, so this is like the type of wine you have, given the amount of some chemical, is a Bernoulli with parameter x over 900. So notice how it depends on your x. Okay, so the amount of chemical is going to change the probability of whether it's Barolo or not. And so how is that going to work? Well, Bernoulli with this type of parameter just is, right, it's like Bernoulli with this parameter is the probability of getting 1 is the parameter. So that's what this, so I'm just writing out like what it means formally. And the probability of getting 0 is just 1 minus that parameter. So like for a coin flip, you know, this would have been like 1/2, and you would have been like the probability of getting 1 is 1/2 here, and the probability of getting 0 is also 1 minus 1/2, which is 1/2. Okay, but there's an intuitive interpretation of this, which is like as x increases, which is the amount of chemical increases, the probability that I get the Barolo wine is also increasing clearly, right? Because like look at the case where x is 0. Well, then the probability that I get Barolo wine is 0. If x is 900, the probability that the wine is Barolo is 100%. So this is telling us something like the more of this chemical, the more likely it is this Barolo wine. Okay, and that's how you should interpret this. And now, like, here's the calculation, which is like someone might come up to you on the street, you know, and be like, well, what's the probability that you know, I got some wine, but the amount of chemical in that wine is going to be between 0 and 50 grams, and that wine is now Barolo. And so that would be this thing here. And you're like, okay, well, and that person's also like, I'll give you the corresponding PDF for X, which is the amount of the chemical, and I'll give you the conditional of Y given X, which is the conditional of the wine given the amount of chemical, and you calculate this for me, and then you go off and you write out this thing, which is this is just writing out the corresponding event over integrating and summing. And then you break up this guy in here because you don't know how to deal with it. You don't have this thing. You break it up into the objects you do have using the chain rule. So that's these two objects. And then after that, you just solve your integral because you've got these functions, and then you just, you do the inner sum first, and then you do the outer integral, and anyways, you do this calculation, you get some percentage. So it turns out for the values given, there's like a 0.15% chance that your wine is Barolo given that amount of chemical. And like, does that kind of check out intuitively? Well, sort of, because I told you that, you know, like if your chemical is 0, there's no chance it's Barolo. So if you increase it to like 50, it's still quite unlikely, even at the highest regions. That'd be like 50 over 900, whatever that is. I guess it's like 5% or something. And then, so it's like, in this region, what's the chance of Barolo? It's going to be quite unlikely. Okay. Is there any questions about that example before we move on to talking about this data set now? Okay, so hopefully with all this like background, it should now almost be obvious what this data set thing is and what it means for it to be independent and so on. So let's do it. So your data set contained n data points, right? There's these like feature label pairs. So I'll write it, the way we've seen things so far is I would have to write like D is equal to n random variables. Let's call them Z1, Z2 up to Zn, right? That's what we've seen so far. But it turns out that these random variables inside a multivariate random variable can themselves be multivariate random variables. There's no problem with that. And so each one of these Z's, right, are these feature label pairs. So these, like every Zi for every index I, is itself a tuple of a feature and a label. So it's itself a multivariate random variable. And then even within there, it's still fine if one of those things is a multivariate random variable, which is like the feature. You can have multiple features. So in the case where you have multiple features, that's also going to be a multivariate random variable. So you can see there's this like, there's this depth to the expression. But it should all be fine, because if you unroll the whole thing, you just have this giant tuple, the data set, of a bunch of random quantities. And we're going to talk about its distribution and so on in a second here. Okay. So is there any questions about that? All I've done is written like the data set is this giant tuple of random variables where you can think of each Z as being a feature label pair. And each one of those feature label pairs is itself a multivariate random variable. Okay, so obviously each one of these things has distributions that we can talk about that we've seen above. So the data set itself has a giant joint distribution, which I'm going to denote by P of D. That's a distribution of the data set. So you can ask like, what's the probability that these things take on some value, which is like are in some event. Okay, and each one of these feature label pairs is going to have a marginal distribution that I'll write as like P of Zi, right? Okay, so that's like the probability that I get a certain feature label pair, or like, yeah. All right, so here are the assumptions now. The assumptions in words are something like every single feature label pair I gather is independent of the others. So it's like when I get a house or whatever, I don't look at it and be like, oh, based on this house, I seem to need houses that have more room. So I go to like some other region of Edmonton and gather houses. It's like, no, I just go and gather each one of them independently without looking at any of the data points I've gathered. And I'm also going to make sure that I'm gathering all the data points from the exact same distribution. So that would mean something like I'm gathering all these n data points from houses in Edmonton independent of one another. It's not like, the first 100 I gather in Edmonton, and it's like, oh, well, actually, kind of want some more from Toronto, so then I go to Toronto and gather some more, and so on. So that's described in this way of the assumptions, which is like each one of these feature label pairs are independent for each one of these i's. So if you were to write like this PD, it's going to be this product. We'll see that in a moment. And every single one of these distributions, so like for every single feature label pair, it follows the exact same distribution. So they're all equal. And this is read as, these feature label pairs are independent and identically distributed. People write IID. And this gives you the following, which is like this data set distribution was very ugly. You don't know how to that would be very awful for me to state what that is for a given example, but it turns out to be a whole lot easier now because you can be like, oh, well, since things are independent, I can write them out as these products, n products. That helps a lot already because now I just need to talk about n marginals. And even better, every single one of these, so let me just maybe make it clear, this is independence. Wow, it's a long word. Okay, and the second property is I can replace each one of these marginal distributions with the exact same distribution, P of just Z. And so this guy here is like the fact that they are identically distributed. And so that turns out to be extremely useful because now I just am going to need to talk about what is the distribution of the feature label pairs. And that's we'll see later that when things are independent and identically distributed, if you I'll put a word out there, want to estimate something about it, such as what's the average value, it's going to be a lot easier when things are independent. And so that's also partly why this assumption is made. Okay, so maybe another thing you might ask is why did we make this assumption? This is surely not true in various cases. And the answer is going to be something like this property is going to give us something very useful later on when we try to estimate let's say, the expected value of something. And because of that that property giving us this useful thing, we're going to be able to design algorithms based on this property and so on and so on. And things, if they weren't independent, then it gets trickier and it's unclear how to do things, but people obviously handle it. And we will not care about that in this course. Okay, yeah, various ways to write this. Point of the story is the way we wrote it above in the very first picture is we wrote it like this. Like, you have the data set. I've now actually plugged in the feature label pairs inside. It comes from this giant outcome space, which we've already talked about in the math review part. Beautiful. And yeah, then you will say something like each one of these feature label pairs, and we write this symbol here, which we've maybe seen before, are sampled or distributed according to this exact same distribution. Notice it has nothing to do with the index I, and they're independent. So that's what you actually had seen at the very beginning. Yeah, and this is in words. Okay, I don't know how many times I can rephrase it, but that is what you want to take away from this. All right, so now we've dealt with the data set at this point, and for the next 30 minutes, our goal is going to be to deal with the remaining two objects, which is going to be the learner and the predictor. Okay, so the learner is a function of the data set, right? So what happens if you have functions, and the data set's a random variable. So what happens if you have functions of random variables? That's the next topic. Well, it turns out that they are themselves still just random variables. Okay, so like obviously this is, it immediately implies that the learner is going to be a random variable, which is kind of weird, right? But we'll talk about it. So how does this work with, once again, simple examples? So a function of a random variable is a random variable. So let's see this with like a six-sided dice, a fair six-sided dice. So, okay, we write this like, you have this random variable x representing, you know, the random roll of your dice, outcome space 1 to 6. Probability of getting any number is 1/6. That's the PMF. Great. Nothing to do with joint anything. This is just like the original. You just have one random variable. And now maybe you, I don't know, someone tells you like, based on your roll of your dice, I'm going to pay you some amount of money. And the way I'm going to calculate the amount of money I pay you is just, I'm going to take the roll of dice, I'm going to square it. So that would be like represented by a function of the random variable x. So something like x squared, right? And now that's still like intuitively going to be a random quantity, right? Like the amount that the person pays you is still random. It's dependent on that dice roll. It's just like some calculation based on it. And so yeah, so this new function is itself going to have like an outcome space. The outcome space is going to be its range. And so yeah, this is going to be the outcome space. You just take every one of the outcomes and apply the function to it. And so you get y, the outcome space for this new random variable. Yeah, and so sometimes people like to give this, they don't write functions of random variables. They like to like say, oh, since this thing's a random variable, I'm going to give it a new symbol and hide the fact that like maybe it's a function. And so they'll write like y now represents x squared. So everywhere I write y, capital Y, I now mean x squared, and you should know that. And that kind of really hides this fact that it's a function. But that is very often done. Okay. Yeah. So here in this case, things are quite simple because like for every outcome of the original random variable, there's a one-to-one map to the outcome of the function of the random variable. So like, for instance, the value of 1 maps directly to 1 squared, 2 maps to 2 squared, and so on and so on. And so the beautiful thing about this kind of case is that if you want to talk about the corresponding, well, like PMF of this random variable y now, well, it's going to be exactly the same because there's just like this one-to-one map. So the probability that, you know, you got 1 on your dice roll, or let's say 2 on your dice roll, is the same as the probability that the person pays you $4 because there's this one-to-one mapping. And that's just saying like the probability of your random variable y is the same as the probability, well, is the same as the original probability 1/6. But that doesn't always have to be the case. So right, in this case, these two are equal. But it doesn't always have to be the case. And let's look at an example of how that might happen. And the story is going to be like you can map to the same, two values can map to the same corresponding value due to your function. Okay, so suppose now that x can be between -10 and 10. And you use the exact same random variable we saw above, which is like x squared. And I don't know, this is a terrible example, but it says like x is the payout from a slot machine. Okay, that's fine. So like x is like maybe you get you get some value from the slot machine when you played between, like, you either lose $10 or you gain $10 relative to how much you paid. And so that would be X. And then for some reason, Y maybe is like, I don't know, someone decides to square the value of your winnings from the slot machine and pays you that much, something like that. But notice the thing is that, like, the values negative, let's look at this, f of like -1 is equal to f of 1, which is equal to x squared, so 1 squared. So they both give you the same value. And so, yeah, so then it turns out that, like, calculating the corresponding PMF for Y becomes a lot more complicated. And so we're not going to talk about it in this course because we actually don't end up needing to use it, as we'll see in a moment, or like actually in a few minutes, we're going to see that we never really need to deal with this object. But I just want you to know that you can't just directly use the original PMF. Like, if your function maps multiple numbers to the same thing, right, like this, well, then you need to handle this differently. Okay. That's this function of random variable stuff. And I mean, there's a process to calculate this, but we're not going over it. Okay, so now we a little more formally see the thing I already said, which is like your predictor and your learner are themselves random variables. So if you have some random feature coming from like some marginal distribution, this is just the distribution of the features now, nothing to do with, like, let's say the labels. Well, then your predictor, let's say you get this new random house. Someone, like, I don't know, gives you a new house. They randomly chose it from Edmonton. And then this function, which is your predictor, is now going to take in this, like, well, it's going to take in this feature, but that's a random variable. And it's going to look like this. Let's say, whatever, this is some function. And that itself is going to be random because, like, look at it, right? It's a function of the random variable x1 and x2, which is a randomly chosen, like, feature based on, well, x1 is the first feature and x2 is the second one. Yeah, so that's going to be a random variable. You might wonder, what does that imply? We're going to see shortly what that implies. But yeah, so you can talk about, like, what's the probability, that my function equals some values or something like this. Okay, and then you have the learner, right, which is like this complicated looking thing that maps data sets to corresponding predictors. And that itself is also going to be a random variable if the data set is a random variable, which as we have seen it is. Right? So, like, ideas like you sample a data set, right? And sampling a data set should be interpreted as you get n samples of feature label pairs independently from the same distribution. So you get this random data set. If you plug it into your learner function, it's going to output some other function, and that function is random, right? It's a function of the data set. And so we've seen, like, examples of it above before, like, based on the data set, this function will change, right? It might be like, I mean, the one function we saw is this, like, memorizing learner, which looks at, if you give it a new feature, if you plug in a new feature into here, you look at your data set and you see, have I seen that feature? If I have, then I output the value. Otherwise, I output, like, 0. Well, obviously, that's going to change if your data set changes. That's all we're trying to say here. Okay, so that's all you need to know. That this is your new, this learner is itself a random variable. Its outcome space is going to be the set of functions. Okay. And so we can talk about things like, what's the probability that the predictor outputs some value or some range of values, depending on what y is, if it's discrete or continuous. And we can talk about things like, what's the probability that my learner outputs some type of predictor? And then we're going to care about how good is that predictor and how likely is it that it is good. Okay, and to kind of finish off, the way we're going to do that is through these objects called, like, expectations and variance. These are going to be, like, somehow maybe the way we measure something. Okay, so expected value, as the word kind of says, it's like, well, actually, maybe this slightly is misleading what it says. So the expected value is, like, you should think of it, it's going to be the average value of your random variable. So, like, maybe the roll of a dice. If you were to do it infinitely many times and take, like, the average of them. Okay, this has some interesting, first of all, if you're taking, like, the average over a bunch of things, the values, like the random variables, must be numbers, and so we're just going to say they must be values. Yeah, they must be real values, right? If you need to take an average, that's going to be important. And it's not always the value we like actually expect to see. It's the value that, it's not the value we expect to see most frequently. And like actually for this dice roll case, you're going to see that the average value of a dice roll is 3.5, which maybe like makes some sense. It's the middle number between 1 and 6. But the problem is that you're never going to get 3.5 on your dice roll. Okay, and the calculation of the expected value is as follows. You look at, okay, so this is how you write it. It's the expected value of a random variable x. And the calculation is like, you just take every single outcome in your outcome space and you multiply it by its corresponding probability. So for the dice roll case, it would be like you take you have 6 outcomes, 1, 2, 3, 4, 5, 6, and you multiply them by their corresponding probabilities, which are all 1/6, and you sum them up. And that gives you the expected value. And for the continuous case, it's just an integral. Okay, so let's see this through the examples. So 6-sided dice, this PMF is 1/6. Let's calculate the expected value of the random variable. It's this giant sum, which I had alluded to, and it's 3.5. And it's not a number you can actually roll. And hopefully this makes sense once again, right? Like you basically look at all your outcomes, which here is only 6 of them. You multiply them by their corresponding probabilities, and then you sum them all up. Yeah. Okay. And for the uniform coin, unfair coin, so here we have like the case where your coin can be biased, it's not 150-50. You would write this like, you have a random variable, can take values between 0 and 1, but the probability of it taking the value 1 is going to be described by a parameter alpha. And we read like it's a Bernoulli with parameter alpha. That means that the probability of 1 is alpha. 1 minus alpha for the probability of 0. And then you can calculate the expected value. Well, it's just a sum of 2 things, right? It's like the probability that you got the value, the outcome 0 times the probability, plus the outcome 1 times the probability. And we get that, the expected value is alpha. So it's clearly not, of course, like you can't flip a coin and get a value alpha unless alpha is like 1 or 0. And so in the fair coin case, this would be like 1/2. And you say the expected value of my coin flip is 1/2. And then it's like, okay, you're never going to get 1/2. But on average, if you averaged all of your coin flips, like if you did that infinitely many times, it would be 1/2. That's what it means. Okay, and then we saw this with the normal distribution. I kind of alluded to this, which is like the expected value of the normal distribution, which had a density like this. All you need to know is that, well, the expected value is it's going to be calculated by this complicated looking integral over all the outcomes times the corresponding outcome x. So you take the corresponding outcome x multiplied by its PDF, this complicated function. You solve that integral, you get exactly mu. You don't need to calculate this, but that's what you should know. So this is the first parameter in a normal distribution. Okay, that's all you need to know for the normal distribution. And okay, is there any maybe questions about that before just a few more steps on this? Okay, so just like continuing, you might care about the expected value of like a function of a random variable. You can see this is going to be the same story. A function of a random variable is a random variable. If you want to talk about its expected value, you better output values that are real numbers. And then you calculate its expectation. And here is a very beautiful fact that you don't, that's going to tell you why you don't need to care about the function, like the function of the random variable's corresponding distribution. Okay, so let me show you first. So the expected value of a function of a random variable can be written as like the sum of the function times the probability of the outcome plugged into the function. And notice here, this is not the PMF of the function itself. Okay, but like, yeah, so it's not equal to that. And notice here we're summing over the outcomes x and not the outcomes that the random variable, which is the function of x, takes. And so this is a beautiful property. You can like show it. It's quite simple, actually. It's like a few lines of just expanding out what the definition is and stuff. But a point is, all you need to know is the PMF or PDF of the original random variable x and then you can calculate the expected values of any function of it. That's what you need to know. Okay, so we can do for like this, you know, payout in the slot machine example, you have this x squared function of the random variable x. And remember we had this, like, I said that like this is the much more complicated thing. This is the actual p, I guess this guy's, well, let's see, what's y? Y is like a continuous random variable, so this would be the PDF. I bet it's complicated. Turns out we don't need it at all, because if you do the calculation, which I show below, if you calculate the expectation using the formula above and just use the original PDF, which was just the uniform one, you can do the calculation, you get 33.33 is the average amount you're going to get if your random variable is x squared and x takes values between this range. And then it turns out if you do this calculation with replacing this function as like a random variable y and then integrating over its range, which is 0 to 100, and using its corresponding PDF, which I'm just telling you, you also get the same thing. And so, yeah, this just shows you, you never really need this thing if you talk about expected values, which is all we're going to be doing. Okay, and then maybe kind of like to finish is, okay, so that's the expected value. And that's like, in some way, you can think about it as it's just like it's a number, right? That somehow summarizes information about your random variable. Okay? And it turns out there's all sorts of like numbers you can talk about. And there's another number called the variance, which summarizes a different piece of information. And as the word kind of implies, it kind of tells you how much does your random variable vary. And this is quantified again by a number. And this is going to be really useful, right? Because like at the end of the day, you know, these random variables have these distributions. They're like complicated things. They can take all these values. But at the end, I just like want, you know, like if I'm going to want to like, let's say pick a good predictor or something, I just kind of want a number that's going to tell me something about it. And then I'm going to want to make that number like, let's say as small as possible. If that number means bad or something like that. Or if it means good, I'm going to try to make it as, so these numbers are going to be useful kind of, I guess, pieces of information about random quantities that you can then, I don't know, like apparently choose to optimize some way. We'll see that. Okay, so variance. So it tells you how much a random variable varies from its expected value. And the way it's written is as follows. So there's this notation, variance of x. It's actually defined through the expected value definition. And it should be read as follows, which is, I'm going to look at the expected value of x, first of all. That's just a number. Okay, so like, this is not random. Important. Right? After you plug in x, you do this whole like sum integral thing, you just get a number. There's nothing random anymore about it. Okay, and then you have a random variable x, and you're going to ask, like, how much does my random variable x vary relative to its expected value? And then because of the fact that, you know, negative things can cancel out positive things, right? If like, okay, let's say the expected value is 0, and then like maybe x takes -1, and then x could take like +1. That seems to be varying, but those could cancel out when you sum things up. So you're gonna like, you'd really want to put like the absolute value, but that turns out to be ugly because it's like a it's a discrete function, like it has this jump, you know, the absolute value. So people just like square things to make it a positive number and to make things smooth. And so yeah, so really all we're trying to do is compare how much x varies relative to its expected value, and then you want it to be just a number, so you square that thing. Okay, and it turns out there was this useful property which if you just expand out using the expectation holds, and yeah. Okay. And this whole thing, yeah, this is just like another function of a random variable. And notice these are all like x has to be a real number. This gives you a number. You square a number, you still get a number, so you can take its expected value. And okay, so that's the variance. And then let's look at what's the variance for some of these examples. So like for an unfair coin, where they had this like parameter alpha, which tells you the probability of getting 1 or heads, you can calculate the variance by first calculating its expected value, which is alpha. We've seen that already. And then the variance is going to be this difference, right, of x relative to this. I mean, what is this? Like by the definition of expected value, it's just like you sum up over all the outcomes of your function. This is your function of the random variable x times the probability, the PMF. And so if you do that calculation, there's only two possible outcomes. You get that the variance is alpha times 1 minus alpha. Okay, so maybe that probably didn't tell you anything almost, but let's as maybe a trick you should learn from this course and stuff is that, like, whenever you get to a mathematical expression and it looks like you have no idea what's going on, just plug in like some extreme values and make sure it makes sense in those values, and then you're like, if it makes sense there, it's probably fine. So here's what we're going to do. We're going to be like, okay, like if alpha is 1, the only thing I can get is heads, right? It's the only thing I can get. Like if alpha is 1, to get heads all the time. What should be the variance? It should clearly be 0. There's no way anything's varying. Does that work? Well, let's try it. So alpha equal to 1. What do I get? I get 1 times 1 minus 1. Beautiful. That's 0 times 1, so it's 0. And here's the other extreme. Like alpha is 0, so the probability I get heads is 0. That means I always get tails. Let's see. Alpha equals 0. Well, I get 0 times 1 minus 0, which is just 0 times 1, again 0. And then you're like, okay, I probably got this right. And then I move on. So this is how you should do your assignments and exams, something like this. Okay. That's, or you could do this other calculation, which is, if you do it, you get the same quantity. Okay, and then we talked about this normal distribution. So for the normal distribution, if you want to calculate the variance, you can imagine how ugly that expression is going to be. It's going to be like, you have to take this thing and then multiply it by its just disgusting looking PDF and calculate its integral. Turns out if you do that, you get sigma squared, which, as I had alluded to before, is the other parameter, and that's exactly its variance. And visually, you can see through the density function that if sigma squared is small, the density is like tighter, and if sigma is big, then it's wider apart. Okay. And yeah, to finish, I just basically tell you how to handle the multivariate case, and then I tell you like a couple little properties, and then we'll be done. So multivariate case is handled in like almost the exact same way, and this is just the expected values. So if you have some multivariate random variable, well then, if you want to talk about the expected value of it, right, you got to have something that's a real number. So you're going to have to talk about a function of your multivariate random variable like this, and it's got to map to a real number, because if you want to talk about, the expected value, it's going to be the sum, and you can't sum up like objects like cats and dogs and stuff. Okay, and yeah, so if you have a function of a multivariate thing, turns out all you're going to need is the joint PMF or PDF or mixture of the two of the original random variables x and y. So right, we avoid this problem again of needing to calculate the corresponding new PMF PDF distribution of this like function of the random variables. And so yeah, so the calculations, there's 4 cases, like if x and y are discrete, if x and y are continuous, or if the other is discrete. And the calculation is as you would expect. You just like, let's look at the discrete case. It's like, okay, I have 2 random variables now. I'm going to sum up over both of their outcomes. I'm going to plug in the function, and I'm going to multiply it by the corresponding joint PMF. And then, yeah, the other cases are the same story. And, okay, let me just, let's see how much time I have in a second. So there's that. There's an example above, which I think I'll leave for next class, because it kind of beautifully leads into the whole supervised learning thing. And so then I just finished with a few more properties. So there was the joint, right? There's like, you can take the expected value of joint random variables. You can also do it for like, conditional things. So you can be like, what's the expected value of some function conditioned on another random variable being something? And that calculation is as you would expect as well. It's like, you take the sum of the function times its corresponding conditional PMF or PDF. Okay, and I leave you with, I just read through a couple of properties. You're going to see them later. You can work them out. Maybe there'll be assignment questions. Maybe there are exercises in the notes. I don't remember. But let's go through a couple of them and just get the intuition, and that's the last page. So turns out that if you have the expected value of a constant times a random variable, so C is going to be just some number, a constant, you can take out the constant outside. And that should be obvious, right? If you write out the expected value, it's like a sum of things. If you just have a constant, you can take it outside of the sum. If you have the expected value of 2 random variables, you can break it up into their individual expected values. Should be also obvious, because the sum is what is called a linear operator. So if you have the sum of 2 things, you can break it up into sums of the other things. And same with the integral. This one's more tricky. I don't even think we ever use it, but I'll just leave it for people who want to work it out if they want. Yeah, maybe we'll see it. If we do, then I'll talk about it then. But it turns out like the expected value of y is the same as like the expected value of y times, or the expected value of the expected value of y given x. And okay. Other things, the variance of a constant, right? A constant's not a random variable, so it doesn't vary at all, it's 0. You can work that out too. The variance of a constant times a random variable, you can pull out the constant as well, because remember the variance is an expected value. But remember it's the expected value of like x minus the expected value of x squared. So that the constant has to get squared when you move it out. And then finally, here are some important properties of when things are independent, which we will definitely use. Which is if x and y are independent, then beautifully the expected value of x times y, which is kind of ugly looking, right? This thing's kind of like the sum. And then you have like, well, x times y. Well, and then you have this thing. Well, then it's really nice because you can break this guy up, as we saw, into p of x and p of y. And this sums over like x kind of and y. And then you can split it up into two parts. So you can split it up into this expectation and this. And you can kind of maybe see that. You just group this with the x and then group the y with the y, and it's fine. And same thing, if things are independent, well, it's not quite the same. It's like if the variance of the sum of things, if things are independent, then you can break it up into two variances. Okay, that's everything. Next time we get into actually working with supervised learning and defining what we want to do, we'll learn that. All right. See you on Thursday.